just use this. Okay. I'm going to talk a little bit about the low energy business and precision tests of the Standard Model. The alternative to materializing particles, of course, is to just use the precise predictions of the Standard Model and do exquisite experimental measurements to test them. Okay, instead of doing like the LHC, actually producing something, you can do Electroweak experiments and see if you can see a deviation from a prediction. Variety of things, the Qweek at JLab, the G-2 EDMs, double beta decay, neutrino beta decay, et cetera, all give potential insights. If you see a difference from the Standard Model, you know you have new physics of some kind. The Standard Model of Electroweak, basically, these are the coupling constants. I'll go through that real brief. I'm not going to say much on it, but there's basically three ways to get at it. You can do precision measurements of the up-down coupling constants, the quarks, the axial vector up-down coupling constants, and the electron coupling constants. And this is a large Lagrangian, and what you do is get experiments to select pieces of this and take it apart. And then you use the whole set of information, which I'll show you later, to see what you can say for things. And this is, of course, the classical experiment by Charlie Prescott and company done quite a few years ago, but they did get a sine squared theta W measurement and the first real evidence of neutral currents and parity violation back then. So it's kind of the benchmark of all of the interpretable high precision parity work. Okay, now you can make a triad of things where you have basically atomic parity violation, weak charge measurements, weak charge measurement on the proton and the electron. So the semi-leptonic sector down here, leptonic up here. These break down experimentally into this, like the SLAC E158 experiment, which did a 13% measurement of the weak charge of the electron. The planned Molar experiment at JLab, about 10 years away, 2.3% is the goal. And then down here you have the famous cesium experiment that did a 0.5% measurement, and another planned experiment to do 0.2%. And then the proton weak charge, we have a preliminary measurement out of about 14% of commissioning data. It's actually about 3 days on the experiment of commissioning data, and we ran for almost a year. And then the rest of the data is being analyzed in a planned Mainz Mesa P2 experiment, which would do a 2.5% measurement, and that's again about 10 years away. This is just an example of how these things, like the weak charge of the electron and the proton, the pulls for new physics are different, okay? SUSY loops, they pull opposite, they would change their signs. Z primes are parity violating SUSY, they pull in the same direction. Leptoquarks, only the proton would be sensitive and not the electron. So you have some internal controls and things like that. This is the state of the running a few years ago, both the wish list of things that hadn't been done and the classic experiments that had already been completed, and of course the stuff nearer at the z-pole. And so the idea is that one of the good metrics to see if you deviate from this line. Now it depends on where you do your experiment in Q squared, so it's the radiative corrections is where the new physics, if there is any, would be hiding. Any disagreement, of course, would be an indication of new physics. And the idea is to push the precision of these as much as possible. Now, the theorists still adjust this occasionally, and the NUTEV experiment, there's still some adjustments on it. This has already been adjusted since then it moved back. Okay, parity violating asymmetry on the proton. The Qweek experiment just recently completed, well, actually a couple of years ago at JLab. Basically, you have the expression for the form factors here for the asymmetry, and although you see this term sine squared theta W, it's actually irrelevant because the axial piece is small. The sensitivity to sine squared theta W actually lives in here. Okay, and what the nice trick here is at these things is if you look at the asymmetry and the scattering, the longitudinal scattering, and you keep the Q squared low and the angle in the laboratory low, and your beam energy is not too high, you can break this down pretty well into expression, which basically has Qweek out front, and then a term here, which is the form factor due to the hadronic structure. And much of this experimentally comes from all the strange quark searches that were done over the last 20 years. So it's good experimental. This would be a slope, if you will. And so it's pretty clean. There are some hadronic corrections you have to depend on theory, but it's a pretty clean measurement. And this is what that apparatus actually looked like. This is a cartoon, of course. This is what it really was. And these are the envelopes. So at eight detectors, the images form on quartz bars. It's an integrating experiment, not counting. So you look for changes in the total current of the system between the difference over the sum. And it had a very high power, 3 kilowatt target, and very low Q squared. And we ran for about a year at 180 microamps and about 89% beam polarization. This is what we got from the commissioning run, which was actually 3 days of commissioning data. This is 25 times more production data we're still analyzing. That'll come out probably in the spring of 2015. From that, and using the atomic experiments, we get a point here, which is about twice the size of the E158 number. This is a safe estimate of what we're going to get in the final result. And we can extract that we charge the proton, which of course agrees with the standard model, the coupling constants for up-down quarks, and the neutron weak charge. Okay, this is the example of the quality of the final data, the full data set. We had 2 major runs. This is run 2, and this is blinded, of course, right now. And this isn't all the data, it's about 70% of it, and that's because this is going in a NIM article that's going to come out soon. But the raw points were like this, the black points, and these were like monthly units of time, which we do systematic checks with. And what's called natural regression, what you do is you unfold all the effects of beam wiggling and intensity modulation and energy changes and things like that are very small, but they travel on the beam. They're correlated. They come out of the injector somehow, even though you try very hard to prevent all of that. And you can get that sensitivity and do that regression, which is the natural, if you will, wiggling or modulation or properties in the beam. You can also mechanically drive it, like you can modulate the energy yourself. A big modulation can modulate position and angle and things like that. And so the interesting thing is that doing these regressions either way doesn't really change the result. And we get a good chi-square on once we do these regressions. So the effects are small but real, and this is one of the gold standards for a successful parity experiment. Do you have a complete model, and is it linear, and does it seem to be valid? And so it looks pretty good, and like I said, we have another run, and the reason this is only 70% is it was cut so that the same amount of data was available for all of these. We have a little more of the data in this class, which is what we'll actually publish. This is sort of a control to validate that this type of regression is good. And now, after Qweek, about 10 years from now, there should be a publication coming out from Mainz. They have a funded experiment to try to go down another factor of 2 in the precision of Qweek. They're proposing, the last time I looked, was to build a solenoid. It would double focus like this. In detectors over here, it'd be big acceptance. They would use 200 MeV, the high polarization, and another high power target. We rent about 2,000 hours. They'll have to run for 10,000 hours, but since they have more or less dedicated facility, they can actually pull that off. This is their figure of merit. What they went for is, well, they were building a low energy machine, so one of the advantages of doing an experiment at even lower energies is that some of the remaining theoretical hadronic corrections, particularly a hadronic gamma Z box diagram, which the theorists estimate between 0.5% and 2% correct uncertainty in it, they're settling down about 1 to 1.5% now. So it doesn't affect our measurement of Qweek at JLab. But if you want to do it a factor of 2 better, you have to get your arms around it. And the price they pay is they have a much smaller asymmetry, so they have to run much longer. But that's been approved, and they're working on it. And the SLAC, and I'm switching things and do polarized electron scattering off atomic electrons. So the very famous SLAC E158 experiment, I'm just going to summarize it real quickly. They had a high power target. It was done about 10 years ago. It achieved 17 parts per billion uncertainty and a sine squared theta W of 0.0013 uncertainty. And it was made out of a spectrometer based on quadrupole magnets. And that's your reference. Now, the next generation is the next generation experiment, a Molar experiment at JLab that uses 12 GeV. Actually, it'll be 11 GeV electrons. That's also about a decade away. It's seeking funding. It's approved, but it isn't funded yet. And The nice thing about that is, unlike the Slack experiment, they chose the kinematics energy very carefully, and they can get both forward and backward events. So they can get almost 100% acceptance rather than 50% for a toroidal effect. They have two toroids. And again, they'll do a Q squared of 0.0056, and they'll be down at around 35 parts per billion, and they want to do, of the asymmetry, they want to do the precision at 0.7 parts per billion. So that's really getting small now, just like the Mainz experiment. It's going down another order of magnitude, both of them. And so it's a competitive number for the most precise Z-pole measurements. So on here you'll see what, if Muller succeeds, what it will look like compared to the others. So it's comparable to any of these other single measurements. So this is one example. If you say the the LEP and the SLC measurements were 3 sigma difference, Muller's comparable. You could actually settle that issue with it. There's other ways, of course, but this is the cleanest way within a parity experiment to do that, and it's probably the only way you're going to do it in the next decade. So it's an extremely precise parity experiment. It's not easy. No one said it is. It'll be very hard to do, but JLab is a beautiful superconducting accelerator, so the beam is very stable, and that's what you need to do these kind of measurements. Now, a recent PVDIS, this is a successor, if you will, to the Prescott experiment. It was done and just published with a 6-JeV beam just before the machine turned off a couple of years ago for the upgrade. And then it used a 20 centimeter long liquid helium, liquid deuterium target, 100 microamps, it was actually about 89% polarized. And here's the kinematics for it. It has 2 points that it took at 1.1 and 1.9 GeV. And it went after the C2s and did a nice job of that. And it was published in Nature last winter. And I'll get back to all of these in a summary in a little bit. Now this sort of begins to summarize it. The nice paper by Erler and company that came out where they took everything except the electron experiments, because they don't fit on this, and made coupling constant sets that allowed you to put them all in the same plot. And this is sort of the neutron weak charge in disguise, and these are other combinations. But for the moment, don't worry about that. The way you read it is these axion vector terms refer to the first and second expression, so a little bit different than what's in the particle data group. But in either case, you can do these separations, and you get beautiful agreement with the standard model. This yellow here is Qweek. This is all existing data. Of course, the final Qweek, it will get very, very small. This is the atomic, and in the end, this yellow will look a lot like that. And then over here, again, they use their data, which is this ellipse coming in, and along with the old Prescott data and Qweek, the commissioning run, and they get this red ellipse. Again, it agrees with the standard model pretty well. Okay, now if you just do a simple metric and throw what's been done so far on the running plot, you get something like this, where this is our point, E158, and the Qweek commissioning point, and this is the PVDIS point. They chose to run it, to evolve it up to the Z-pole when they published it for comparison, so you can plot it. We didn't do that, so I plot it here. Like I said, this is a safe number for our final precision, I think. And now, the next generation beyond this wants to use the proposed solid detector, which is another big project at JLab. It's been approved by the laboratory. They've got approval to take and ship the Clio magnet, which is what the superconducting solenoid would be. It's seeking funding. It's not funded yet. Part of the program is to do the PVDIS. It's by no means all of it. And what they have to do to do extremely high precision, improve it a lot to be competitive with like Molar and the other experiments, is they have a lot of challenges. They have higher order twists, charge symmetry issues, part-on distribution function uncertainty, and high precision polarimetry requirements. So that's a very ambitious project, okay? The way they plan to do that, they've done some measurements already. They think that by taking enough measurements and basically taking the systems apart, they can separate the higher twists, the C quarks, the charge symmetry violation pieces, and focus on a standard model test, a sweet spot, and take all that out, okay? But you have to do those corrections extremely well, and so that's their goal. Now, again, this is an example of what they are proposing to be able to deliver. Again, these are all, in the case of what's referred to as Qweek, that's our final projected number that they're using. So all of this scale is getting far more precise. So again, you can see how the other experiments, they're huge on the scale of the new stuff. So again, this is assuming the standard model, but this is the level of precision you'd get from the 11 GeV PVDIS. And again, this is on this scale for the C2s, it's less sensitive to C1s. On the C2s, where its real sensitivity is, it's a narrow band, okay? And so these are very nice things, but it will take 10 years plus to get this information. Again, I tried to put everything up here on the same plot. This is the standard thing, it's up to date. I got this from Heidi Schulman, and this, I put the PVDIS point on it that exists, and above this are all stuff that isn't published yet. We're very, very close to publishing, so I made it slightly green, and the others are about 10 years away. And so these are the relative precision you'd get if you just want to use sine squared theta w as your metric. And of course, nobody says you can't average all these together. And now this is a table. I don't want to go over the numbers. What I want to show you is that there was a nice summary also done by Erler and company where they took all the existing experiments, which are up to here, and then the ones that are planned, put them on the same one, did % precision, the sine squared theta w uncertainty, and an angle, which I'll explain in a minute, and I put down what they were and published and everything. And then this is the lambda over g, which for a 95% confidence level. This uses a formulism that tries to be analogous to what Peshkin and company did many years ago, an attempt to try to make these results comparable to high-energy collider numbers like LEP numbers, okay? And so this is in TeV, so it depends on what your G is, of course, but you can just make a standardized G, which people do, but you don't know it until you materialize something. Now these are nice little plots. In their paper, it was all put on one. I've separated the two. So these lines indicate for any particular experiment indicated here the relative pull of these when you have them. This is just data that already exists. Okay, so again, 5, 10, 15 TeV over G, but what they say is that the square root of 4 pi is a coupling constant that would allow you to do a more or less direct comparison to, say, the LEP2 numbers. So you could get exclusion zones or sensitivities at the 30, 10, 30, 40 TeV range doing this. Okay, so this is much more powerful than these numbers would lead you to believe. And the angle, of course, is just rotating around here for these two different combinations. And so like Qweek, when we finish and publish, it'll pull this blob, it'll distort it quite a bit, okay, and pull it farther out, and the same thing for the other experiments. And now, you can get some new physics scenarios, okay? Marciano obliged us. If you want a dark Z, him and his students have done something at 150, 100, 300, 500. This even uses the restrictions from Babar, so that doesn't wipe you out. And whether it can explain G minus 2 or not, I don't know. We'll find out eventually. But anyway, there's things you can do, and this is not the minimally symmetric. This is how this is how Marciano does it. And so you see the sensitivity of the existing Qweek, and the size of our final one will be about in here somewhere. I guess it's shown on this one. It'll be about in here. And then, it's shown here, sorry, the anticipated. And then a Molar number, which would be much smaller. So these are examples of the things you can do. Now, this is current. I don't know what all this will look like in 10 years. Your guess is as good as mine, but it's where we are now. A caution, okay, a brief history of these experiments and a relative experimental difficulty, okay. As you get smaller in asymmetry, it goes this way. These are the experiments plotted along here, mostly according to time, because people do harder ones as time goes on. You have to have higher precision, and that's what they go for. And so this is from pioneering to the future experiments. So we're here, this is E158, these are the earlier experiments. There's a bunch of stuff for strange quarks, and this is the classic Prescott experiment. So you see this is a log plot. So when you make log-log plots of things, you have to say the trend line extrapolations may hit unforeseen limits. That's always the case in these experiments, that you may peel back a skin of the onion and find something that's hard and bitter that you have to get through. But so far, people have made steady progress, and the machines are excellent to do these things. So there's a better than even chance it'll keep going down for a while. And again, I go into here. I give you, in this case, the precision required. This was 10 parts per million on SLAC that they came up with. All the strange quark searches, which we actually use for our background corrections, hadronic corrections in Qweek, are a quarter to 2 parts per million. Then you change to parts per billion, the present test. SLAC 158.17, Qweek about 6. JLab Muller, 0.8, Mainz 0.34. That's getting hard. Now, I've switched topics altogether now. This I got from the Babar folks. They wanted me to make a plug for them, and I will. They basically say the new minimally supersymmetric model predicts 7 Higgs bosons, and they have some comments about that. And basically, they have done a number of studies. I am no expert on what they've done, and they gave some talks earlier in the other sessions, and they see no significant signal at this time. Now, another thing, G-2, that experiment's going to be repeated. Everybody knows it has a 3 sigma discrepancy with theory, but one of the things that'll be needed for it is additional theory. You always use better theory, right? And not everything can be theoretically determined. So these guys are measured a number of things, which they think will be very helpful constraining that and tightening that up, so that when that measurement's done, it'll be more interpretable. And they're trying to do a comprehensive set of those measurements. And again, they have a number of publications on it. And they're the only experiment to measure low energy cross sections from threshold to 4 to 5 GeV. And they are out to do it as best they can. And some channels are still missing or measured with low statistics, but they're going to get them eventually to full statistics. So that should be a big help to the G-2 understanding, at least the theoretical aspect of it. Now, this is all I have to say as a conclusion. They're very complementary to direct searches. I think, it's another way to get there, and people can do very, very precise measurements. And if a direct observation is made, precision measurements may be essential to quantifying the properties of any new particles. I don't think there's any real dispute there. However, there are no guarantees. You have to be careful what you reach for. You can get this can, or this can, or this can. Remember, Pandora's box also contained hope. So, and that's my talk.
Thank you very much, Roger. So unfortunately, we are out of time, and I'm sorry, it was a very exciting but long session. So let's thank Roger again, and please, if you have questions, contact him during the coffee break.